Alrighty, in this video we're going to go over the main equation that relates enthalpy, internal energy, and work, and a few derivations thereof, and go over some very important exam problems. And just a note, I've got tons of videos on thermodynamics and other aspects of chemistry as well. Okay, let's begin. Alright, so we have a chemical equation right here where we have a solid, and the solid's in a container fitted with a piston. And what happens is when this reacts, it creates another solid plus a gas, and the gas pushes on the piston and performs work. Now, the enthalpy change is less than zero, which means we have heat transfer from the system into the surroundings. So let's look at what's going on with the internal energy. Well, the change in enthalpy is equal to the change in internal energy plus the pressure times the change in volume. Now, this is true for a constant pressure process, which is good here because we're assuming that the atmospheric pressure is not changing uh, over the course of the reaction. So this is also the change in enthalpy is equal to the change in internal energy minus the work. And this is true because work equals negative P delta V for constant pressure process, and we're assuming no other work, no electrical or any types of work. So what's happening to the internal energy is, well, this is negative. Work is negative because the system's losing energy as work. So work is negative. That makes this whole thing positive. If we move it to the other side, it's negative. That means the change in internal energy is going down. It's decreasing. We could also look at this using the ideal gas law, where PV equals nRT, and P delta V equals the change in moles times R times T. And we can literally substitute this in to our equation right here of enthalpy. The enthalpy change equals the internal energy change plus RT delta N, because the work done is due to this increase in moles of gas. All right, so that's it for the equations. Let's work on some real exam problems and convert between the two. Okay, here's our first exam problem. We want to calculate the change in internal energy in kilojoules per mole at 25 degrees Celsius for this chemical reaction, and this is the balanced chemical equation. And we're given the enthalpy change, or the reaction enthalpy of the reaction, is negative 1,310 kilojoules per mole. It's negative, which means it's exothermic, and this superscript 0 means that it's occurring under a standard state of 1 bar. Okay, so we're going to start off with our equation. The change in enthalpy equals the change in internal energy plus the pressure times the change in volume. Now, we're not given any information about pressures or volumes, so we're going to rewrite this the other way. Change in internal energy plus the change in moles, RT. And we want to solve for the change in internal energy. So change in internal energy equals the change in enthalpy minus the change in the moles times RT. Now, to get the change in the moles, this is a change means final minus initial, right? Final minus initial. So after this reaction, we have products. So it's moles of the products minus moles of the reactants. But it's not just moles of products and reactants, it's only the gases that we care about, because the gases are what produces the work. So N products minus reactants, so that would be 4 moles of gaseous products minus 6 for the reactants, 6 moles because we add them all up, 1 plus 5 here, 6, so that equals negative 2 moles. That's the change in moles every time 1 mole of this reaction occurs. So we're going to plug that in. The enthalpy change is negative 1,310 kilojoules per mole minus negative 2 moles for the change in the moles. R, now because we're dealing with energies, we want to use the R that has joules in it. 8.1, 8.13, there we go, 134 joules per mole Kelvin. And the temperature is 25 degrees Celsius. We need to be in Kelvin, so we'll put in 298 Kelvin. Now we have a problem here because this is in kilojoules and this is in joules. So we can't just subtract these terms or add these terms. They're not like terms. So I'm going to times this by 10 to the 3 because there's 1,000 joules in a kilojoule, and I'm just going to change that to joules. I hope that's not confusing. So we'll just make this 1,000 times larger because we want to convert it to joules. Oh, actually, you know what? We don't want to convert that to joules. We want to convert everything to kilojoules. So we'll leave this in kilojoules because the questions ask for kilojoules. Since this is in joules, we want to have multiply this by 1 kilojoule divided by 1,000 joules so that joules cancel out and we're left with kilojoules. Okay, so negative 1,310 minus, big bracket here, negative 2 times 8.314 times 298 divided by 1,000 is negative, so it doesn't change much. Negative 1,305 equals negative 1,305, and we're left with kilojoules per mole. Now, this mole cancels out with this mole in some ways. So it looks like this is just in joules, right? It looks like this is just in joules, and this is in kilojoules per mole. So it looks like we can't just add these reactions together, or these two terms together, but we can. This is because this is per mole of the reaction, and this is also per mole of the reaction. So every time, this is like mole, this is the change in moles for every 1 mole of the reaction. So this is moles of products minus reactants. We could even think of this as being divided by moles of the reaction, and that's what this is, moles of the reaction. So we get negative 1,305 kilojoules per mole every time 1 mole of this reaction occurs. I hope that's not confusing. I hope that makes sense. Let me know if it is. And there we go. So we can quantify what the work is. The work is approximately, it's positive work because this has to go down. Work is approximately approximately 5 kilojoules per mole of the reaction is the work there. Okay, hot dog. All right, for our last exam problem, and this is a harder exam problem, we want to calculate the change in internal energy for the combustion of 1.20 grams of octane, which is C8H18 at 298 Kelvin. Okay, so we're given a balanced chemical equation, and we have the enthalpy change for the reaction. This is the standard enthalpy change, or the enthalpy change of combustion, the heat of combustion for this reaction, all of that's the same stuff, under 1 bar is negative 5,470 kilojoules per mole. So we want the change in internal energy, so we're going to use the same equation like we did before. The change in enthalpy equals the change in internal energy. And then this time we're going to go straight to the change in moles times RT because we're not given any information about pressure and volume. So we want the change in internal energy, so we'll solve for that, equals the change in enthalpy minus the change in the moles times RT. Now, we'll plug in what the change in enthalpy is, negative 5,470 kilojoules per mole, minus the products, minus the reactants of the gaseous, only the gaseous compounds, because the gases are what creates the pressure or reduces the pressure. So now you might be wondering why this water is not a gas. So when this reaction occurs, we do produce gaseous water, but at 298 Kelvin, the water is a liquid. So you can imagine when this reaction occurs, it may heat up, but initially you're at 298 Kelvin. It reacts, heats up, and then it cools back down to 298 Kelvin. These are the products back once you're back at 298 Kelvin. So water would be a liquid. So we don't include it. So the change in moles would be 16 moles minus the moles of the gas. So there's 27 moles. And again, this is per mole of the reaction. So if you think of this per mole of the reaction, so every time 1 mole of this reacts, we need 2 moles of octane, 25 moles of oxygen, and we produce 16 moles of CO2 and 18 moles of water. So this is very, very important to get your stoichiometry right. So even though this is moles, this is actually the moles of your products minus reactants every time a mole of this reaction occurs. So that this mole is the same as this mole right here. Okay, R, we want the R that has joules in it, 8.314 joules per mole Kelvin, and the temperature is 298 Kelvin. Okay, so we'll plug that into our calculator. Actually, what I'm going to do, I'm going to do the second term first because the second term gives us the work. So 16 minus 27 times 8.314 times 298. That's negative Now this is in joules, right? This is in joules. So if we want it to be in kilojoules, we would divide this by 1,000. 1 kilojoule for every 1,000 joules. So I'll do that right now. Actually, divided by 1,000. So negative 27.25. So negative. Now this is negative. So we're subtracting a negative. So I'm just going to make this positive, right? This is negative, but this whole thing is negative. So we have subtracting a negative makes it positive. So we have 27.25. So plus 27.25. And in terms of our units, these moles cancel out with these moles. We have joules cancel out with joules, and Kelvin cancels out with Kelvin. So we're left with kilojoules per mole. That's kilojoules per mole of the reaction. That's super important. It's kilojoules per mole. Actually, I'm going to write mole of the reaction right here because we're going to need to differentiate between that. So this is 5470 kilojoules per mole. The work done doesn't change too much. And this is the work done. So this here, this is the work performed by the reaction. Work equals negative P delta V for a constant pressure process. If there's no other work, just pressure volume work. This is equal to negative nRT. So this truly is the work done per mole of the reaction. Now we can add these two terms together, negative 5470 plus, negative 5470 plus 27.2 is negative 5442.8, negative 5442.8. The moles of reaction, I'm going to write that in here, kilojoules per mole of the reaction. So this is our delta U per mole of the reaction here, but we want it for 1.8 grams of octane. So we're going to convert these moles into grams of octane. So we're going to start with this number right down here, negative 5,442.8. We're not significant to that many digits, right? We have, well, 3 sig figs, so actually we'd have 3 sig figs here, 3 sig figs here. So we only have 3 significant figures of 3 significant digits. That was a hard one to say. Okay, kilojoules per 1 mole of the reaction. Now we want to get to octane, right? So we want to cancel out moles of the reaction, and we want moles of our octane. So that's C8H18, I think it is. Now, for every 1 mole of the reaction, every time a mole of the reaction occurs, we need 2 moles of octane. So it's a 1-to-2 ratio. Now that we're in moles of octane, which is what we want, we can get to grams. So we'll use the molar mass. We want to cancel out moles of octane. I always do the units first. If you do the units first, like I'm doing here, you can always see that they'll cancel. So that at least we got our unit analysis right. So, and we want grams of C8H. It's H16. No, H18. 16. Oh, I did 16 again. There we go. Holy. All right. So for every 1 mole of octane, we got to use the molecular formula to find out what the molar mass is. I just Googled it just to make it quick and easy. You can get it from the periodic table. So the molar mass of octane is 114.23. So 114.23. And then our moles of octane cancel out, which gives us kilojoules per gram of octane, which is what we want. Okay, so we'll plug this in. I got this number right here already, so I'm going to keep that in my calculator. Divided by 2, divided by 114.23, and that is negative 23.8. Now we have 3 significant figures, so yeah, negative 23.8. This is significant to here, to this decimal place, or place value, negative 23.8 kilojoules per gram. Oh, we're not done. We're not done, right? We want it per 1.20 grams of octane, not per gram of octane. So let's get to, we got to multiply it by 1.2. So negative 23, oh, sorry, this is kind of messy here. Negative 23.8 kilojoules for every 1 gram of C8H18. We want to multiply that by 1.20 grams of C8H18 so that our grams of CH818 cancel out, and we're just left with kilojoules. So that's how many kilojoules are released for this many grams. And we still got the number there, so times 1.2. Oh, times 1.2 is negative 28.6, because we have 3 sig figs. So negative 28.6. Negative 20. Yeah, that's right. Negative 28.6 kilojoules released for every 1.2 grams of octane. Sweet beans. All right. Hope you enjoyed it. I got so many other videos on thermodynamics and other aspects of chemistry, also in physics and math. So thanks for watching, and good luck on your exams, midterm, final exams, and I'll see you in the next video. Cheers.